Okay, today we're going to learn about our last type of electron configuration, and that is the dot diagram. So I'm going to show you the general form of the dot diagram first. X could be any symbol of any element off the periodic table of the elements. And then around it, you're going to put dots that represent the valence electrons. The maximum number of dots you will put on anything is 8. And that's because the valence electrons are the s and p electrons that are in the outer shell. That includes the 2s and the 6p maximum. So we're going to put them in a specific spot. And you have to be careful because if you see these taught in another situation, they might not concern themselves with where they put the dots. But we're going to concern ourselves and put them in the right spot for the reason that when we get to bonding, this is going to be helpful to us. So our first s electron is going to go in this position here. So the first s goes here, the second s goes here. And then we're going to start putting p electrons, and this is the one you're going to see different. So it doesn't matter if you put the first p1 on the left side or the right side, either way is acceptable. What we're going to focus on is putting the second p1 down here. And that's because of Hund's rule. So that indicates that each of the sides is an orbital, and each orbital will get one electron before we double up. So as long as you give each side one electron before you give any side 2 electrons, it's going to be acceptable, like such. So this is the general form of the dot diagrams. So these are only for valence electrons. Now remember, if we have the representative elements, those are in the S and the P block, they're followed by A. So the S block is the alkali metals and the alkali earth metals over on the left-hand side. The P block is the boron family all the way through the noble gases. So let's do an example of each representative element from each group. I'm going to pick the third principal energy level just to be a little bit different. So potassium has a complete electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember, we identify the valence electrons by the highest principal energy level or the largest coefficient, and the S1 electron is potassium's valence electron. You'll see potassium is in group 1A, so he's going to get 1 dot for his dot diagram. This is the dot diagram for potassium. Let's go to the next element over, which is calcium. I'll do the abbreviated version from now. Calcium has a Z number of 20. I'll back up, and each of the elements are going to have argon as a core, and then 4s2. These are valence electrons. You'll notice that calcium has a Roman numeral 2A at the top, so he gets 2 dots for 2 valence electrons. Let's go over to gallium. His electron configuration is argon, because I backed up to the noble gas and I still get argon, and then 4s2, 3d10, 4p1. Remember, I find the valence electrons by looking for the largest coefficient or the biggest electron shell. That's the 2 s and the 1 p electron. So I'm going to have 3 dots for 3 valence electrons. You'll see the Roman numeral 3 followed by an A. So his dot diagram is going to be like such. If you did it like this, that is also acceptable. Let's go next to germanium, obviously named after Germany. Some scientists' home country, I'm sure. Complete electron configuration, identify the valence electrons, or you look above germanium and find out that he has a Roman numeral 4. The other thing you can check is that he has the valence electrons just like potassium and calcium and gallium and germanium. So that's 2 S's and 2 P's. Just have to be careful that they're not on the same side. So what would be incorrect is if you did this, because that would make it look like he has 2 pairs of electrons, but he does not. He has 2 unpaired electrons and 1 pair of electrons. Next, let's go to arsenic. Argon in brackets, 4s2, 3d10, 4p3, 5 valence electrons, Roman numeral 5, 1, 2, 3, 4, 5. I'm going to give each side 1. Now we have 2 s electrons on the top and 1 p electron on each side. This shows that arsenic has 3 unpaired electrons. Next is selenium. Total of 6 valence electrons, Roman numeral of 2. Let's put the 2 s on top, and then one of them is going to get paired up. So now selenium has 2 pairs of electrons and 2 lone unpaired electrons. Next is bromine. Total of 7 valence electrons. Like such. And then we have krypton. Now krypton has no valence electrons, so he could be written like this, or he could show that this means the same thing. Now, in order to be able to identify that krypton that we're doing a dot diagram, we're going to indicate the dot diagram with 8 dots. Otherwise, it wouldn't look like a dot diagram, and we wouldn't be able to tell that. So this is going to be for krypton. So let's circle these so you guys don't get confused between the different dot diagrams. And everybody in the same family is going to have the same dot diagram. So everybody in the alkali metals will have 1 dot. The alkali earth metals will have 1 dot. Everybody in the D and the F block, all the transition metals and inner transition metals will all have 2 dots. The boron family will each have 3 dots. The carbon family will each have 4 dots. The nitrogen family will each have 5 dots. The oxygen family will each have 6 dots. The halogens will each have 7 dots, and the noble gases will each have 8 dots. So I did look up germanium, and it was named for Germany, and it was discovered by Clemens Winkler, and it is used as It was used as early transistors. It's a silvery white semi-metal. It is brittle. So germanium is a semiconductor. It's used in alloys that makes it so silver does not tarnish. It makes it so it is a little bit harder. It says their oxides are transparent to infrared radiation, so they're used in infrared spectroscopes. So it is very rare, but it's interesting that it was predicted before it was discovered. It was predicted by Mendeleev and before it was discovered by Winkler. I also wanted to clarify, I think I might have said something incorrect. So all of the alkali earth metals get 1 dot. Anybody in the same family as potassium, like sodium, rubidium, cesium, lithium, get 1 dot. The alkali earth metals get 2 dots. Magnesium, calcium, strontium, barium get 2 dots. Anybody jump over the transition metals to the third group. Anybody in the third family or group get 3 dots. Fourth family or group get 4 dots, so on and so forth. The transition elements, everybody in the D and the F block, only have the 2 s electrons, so they're considered to have 2 valence electrons and will have 2 dots. So any element in the center, in the D block or the F block, like iron, cobalt, nickel, all have 2 dots.